Hello, you are welcome to this video, a short video for solutions to problems on elastic properties of solids. I believe with this short video, students will be able to understand a step-by-step approach in solving problems on elastic properties of solids. In this short video, we'll look at questions on Hooke's law of elasticity, Hooke's law will be looked at, stress will be looked at, stress on elastic materials, strain will be talked about, Young's modulus, Young modulus will be discussed. Also, energy and work done by elastic materials. In all, there are 4 questions in this short video to help students understand how elastic materials behave. This is question 1. First, we'll start with what we are given in the question. So in this question, as a rule in physics, you try to itemize the data. Force is given as 40 Newton. The original length of the wire is given as 4 meters. The diameter of the wire as 2.0 millimeter. As usual, we like to work in SI units, so these two you divide it by 1000 to convert it to meter, and that will give us 0.002 meters. So that gives the diameter. Also in this question, we are given the extension as 0.24 millimeter. So the extension is 0.24 millimeter. Also, you convert it to meter. To do that, you divide it by 1000. And that will give 2.4 times 10 to 10 to the power -4 meter. So with this data, we can now begin to do our calculations. The question asks you for the stress, the strain, the Young's modulus, and the energy. So to calculate the stress, first we need to calculate the area. Area is pi d squared over 4 since it's a circular base area. So you have pi, you have the square over 4. So this gives us the area of the material. So with this, you can have your pi as 3.142 multiplied by the diameter, which is 0.002. Then you remember to square that, or you multiply by itself, 0.002. That takes care of the function of the square. Then divide this by 4. So all of this put together gives us area as 0.02 squared times 3.142 divided by 4. And that gives us 3.142 times 10 to the power minus 6. Okay, that gives you remember to put your unit as a standard in physics, meter squared. So that is the area. After calculating the area, now we can calculate the stress. So we know that stress, either compressive or tensile stress, is force per area. So from here, we can calculate our stress as 40 divided by the area that was just has been calculated. I just copied from here. I put it down here. So with that, we can get our stress. 40 divided by 3.142 exponential negative 6. And that will give us 12. Okay, that can be written as 1. That as 1.27 times 10 to the power. So you just get the function for the power. 10 to the power 7. Remember to put the units there. The unit of your stress is Newton per meter squared or Pascal. So Newton per meter squared will do. So this is your stress. Now the next is to calculate the strain. So strain, so your strain, I just copy this down to establish the formula for strain. So strain is defined as extension over natural length. So with this, we can calculate the strain. The extension of the material divided by the natural length. So again, so the strain now equals the extension. Extension is 2.4 to the power minus 4. So that should be a division. So you have 2.4 times 10 to the power minus 4 as the extension. Natural length is 4. So if we do this very well, we should get a strain. So the strain is 2.4 exponential minus 4 divided by 4, that's 6 exponential 5. So we have it as so we put that here, you have 6 times 10 to the power minus 5. Notice that strain has no unit, so you leave it that way. So this is the strain. Next, you're asked to calculate your Young modulus. So it's important for you to remember that Young modulus is a stress over strain. So your Young modulus, would like to write it as, okay, maybe we should write in full for now. Young's modulus, okay, is defined as stress divided by strain. So that's your Young modulus. So from here, if we let our Young modulus be y, we have calculated our stress. So this is this is your stress value here. You copy that value and you write it there for stress. So that divide by, so you have this, so you can put this in brackets. So this now divide by your strain value. This is the strain value here. Copy that and you put it there. That's your strain. If you do that mathematics with your calculator, you now get your strain as using your calculator 1.2 exponential 7 divided by 6 exponential negative 5. And that should give you 2.12 exponential 11. So you should be getting your so you should be getting 2.17 times 10 to the power. So you have 10 to the power 11. So that is a Young modulus, and the unit is Newton meter squared. So this is the answer for the Young modulus. And lastly, we're asked to calculate the energy. So the energy formula, you can use your W as energy is half F times is half Fe, right? So if we apply this formula, see that your work done is half multiplied by the force, which is 40, then multiplied by the extension, and the extension is 2.42 times 10 to the power negative 4. So if you put that value there and you compute that, you should get your work done in the elastic material. So equals, if you just apply a calculator, 2.4 exponential negative 4 multiplied by 20, you should get 4.8. 4.8 times 10 to the power negative 3. 4.8 times 10 to the power negative 3. 10 to the power negative 3. Remember to put your unit as joule. So this is the solution to question 1. So question 1 asks you to calculate the stress, the strain, the Young modulus, and the work done. So we'll now look at question 2. Let me allow you to look at the question 1 again. This is the question: a force of 40 Newton applied at the end of a wire of length 4 meter and diameter 2 millimeter gives an extension of 0.24 millimeter. So you're asked to calculate the stress, the strain, the Young's modulus, and the energy stored in the material. Now, pi value is also given to you. Solution: you declare your data. The force is 40 Newton, the length is 4 meter, the diameter is 2.0 millimeter. You divide it by 1,000 to make it a meter. and the extension is 0.24 millimeter. You divide by 1000 to make meter. So the first step is for you to calculate the area. After getting the area from this geometric formula, pi d square over 4, you get the area to this value. Now you use the area, the answer in the area to calculate your stress. Stress is force over area. And after getting your stress value, you now also look at your strain. Strain is extension of a natural length. This is your strain value. Now you put the values for your extension, you put the value for your length, original length, you evaluate that and you get your strain. Now you're asked to calculate your modulus. Your modulus is the ratio of stress to strain. You have calculated the stress and the strain, you put the values and you get your modulus. Remember to put your unit, Newton per meter squared. And lastly, you have to calculate the energy stored. And that's what you have done by using half Fe to get your value. Okay, let's look at the second question, question 2 in this series. Now, in this question 2, we are told that a force of 500 Newton is applied to the free end of a spiral spring of force constant. This and calculate the energy stored in the material. So, solution. So as usual, the first thing you do is to declare your data. In this question, F is 500 Newton. Now, the next thing we're given is the force constant, that's our K value, as 1 times 10 to 10 to, okay, power 10 to power 4 Newton per meter. Newton per meter. Okay, if you look at the units in the question, it is written here per meter squared is a mistake. Let's quickly correct that. It is per meter, not per meter squared. So we correct this from here. So now we have calculated, we have declared our constants, our values. So the next thing now we try to look at what we are asked to calculate. We're asked to calculate the energy. So that's W, the work done is unknown. All right, so from here, let me put this so that it can align with the other data. Good for our work to align. So from here, we'll first apply Hooke's law to get our extension. So from Hooke's law, from Hooke's law, we can apply F equals to KE. This is to get our extension. So for the F, we have our 500 equals to the K. You have your K. You copy the K, you pick the K value here and put it here and multiply that by your extension. And your next step, you have your extension equal to your 500 divided by your K value. Now, if you do this very well, we should get our extension as 0.05. So that's the extension. I've calculated the extension. You can now calculate your work, which is half Fe. So from here, we can calculate W. So equals to half. You multiply that by your F, which is 500. You multiply that by your E extension, which is 0.05. And if you do that very well, you should get to 15 times 0.05. 12.5 joule. That is the solution to this question. So let's take another look at the question. We are told that a force of 500 Newton is applied to the free end of a spiral spring of force constant base, and you have to calculate the energy stored in the stretched spring. So as usual, you declare your data. The force is 500 Newton. You declare a constant and the W is unknown. So from Hooke's law, you apply a Hooke's law to get the extension. Having calculated the extension, then you use the extension value in your work formula function to get the work done, which is the same thing as the energy. Okay, that answers that question. Now let's look at the other question. This question, which is question 3. The question 3 here. We have that if a force of 40 Newton stretches a material of original length of 0.2 by this, determine the total length. Okay, so for this question, we have a number of things to calculate. So in this question, I will just shift it up here. So in this question, as usual, we declare our data. So solution. So you have the force, it's 40 Newton. You have the original length. Okay, Newton should be capital letter N, so we'll replace this with big N. Now you have your original length. I like to write that as 0.2 meter. So your original length is written as L1, 1 being the initial condition, is increased by, so this material is increased by, so that's the increment is your length extension, 0.05 meters. Determine the total length, so we're looking for a certain length now. Certain length, that's unknown. When the applied force, when force is 30 Newton, we're told that Hooke's law is obeyed. So since Hooke's law is obeyed, the first thing is to use the first set of data given to calculate our force constant. So from this relationship, we can now say since our force is 40 Newton, K multiplied by extension, which is 0.05. So from this, we can calculate our K as 40 divided by 0.05. And from here, we can get our K to be 40 divided by 0.05 to be 800. 800, we'll put our unit of K, which is Newton per meter. So Newton per meter. So this is our K. So since Hooke's law is obeyed, now we'll write F equals KE again. For this second relationship, our F is 30 equals to the calculated K, which is 800. Now multiply by the extension due to the 30 Newton force. So from here, our E equals to 30 divided by 800. So this should give us E as, so 30 divided by 800, 0.0275. So this is the extension that is obtained, all right, when the force of 30 Newton is used. So the new length equals to original length plus extension. So this makes sense. So when you add the extension to original length, you get your new length. So that means L equals to original length, which is 0.2, now plus the extension 0.0375. So if I do this very well, my new length should be 0.2375 meters. So that is the answer to this question. Let's look at the question again. We are told that if a force of 40 newtons stretches a material of original length 0.2 meter by 0.05, determine the total length of the material under a force of 30 newtons. So you see, when a force of 4 newton, 40 newton was used, we got this extension. All right, so you use these two information, the force and the extension, to get the force constant. And when you get to force constant, since the force constant stays the same, you use the force constant now with the new force applied to get the extension due to this new force. And you add the extension to the original length, and that gives us the new length. Okay, let's look at the last question for this series. This is a series. In this question, we are asked to use the data. Let me just pull it up. Okay, let me pull it up. So from here, we're asked to do two things. First, to determine the force constant, and secondly, to determine the work done. So solution. So for a graph of force versus extension, it is important for you to know that of the slope of the graph represents the force constant, and area under the graph is the work or energy. So this principle, you need to remember that for me to get my force constant, I determine the slope, and for me to get the work done or the energy, I determine the area under the graph. So since this graph has been given to us, to get the force constant, we simply get the slope. So slope of the line. So from our knowledge of mathematics, we know that slope of the line is a change along the vertical. Is change along the vertical over change along the horizontal. So change along the vertical, that's change in F, over change along the horizontal, that's change in extension. Okay, so if I do this very well, so my slope, which is the K, so change along the vertical, looking at the curve, you can pick any 2 points along the vertical. I like to pick 50, 50 and 0, then 10 and 0. So those are the coordinates of the points we are going to use. So having this can be, so going back to change along the vertical is 50 minus 0. Change along the horizontal is 0.01. That is 10 divided by 100. That's 0.1 minus 0. So if you do this very well, your K will now be 500 Newton per meter. So this is the force constant. Now the work done is obtained as area under the graph. So since the graph is a right angled triangle, so it's a right angle triangle, so the area is half times base times height. So from this data, We can have it as half times the base is 10, the base of the triangle. You can see this triangle. The base of the triangle is 10, which is 0.1 in meter. It is centimeter. When you divide 10 by 100, you get 0.1. And the height is 50. So we come down. So the half times base 10, which is 0.1 in meter, multiplied by the height, which is 50. So if you evaluate this, you get 2.5. So 2.5 joule. So that is the work done. The work done or energy store. So this is the answer to the question. So I hope that with this solution, you have seen the step-by-step approach to solving questions under electric property. So thank you for listening. See you again next time.